So we'll go ahead and start with one of our theorems about continuity. If a function is differentiable at a given point, then it is continuous. Now, the alternate of that is also true. So if at any point in time you have a discontinuity in your graph at a given value of a, then f prime of x is not differentiable at a. So we're going to talk about the derivative of piecewise function and what that means. Now, these are all three lines, and this is what the graph of this particular function looks like. Now, what can we say about this function? This function is continuous from negative infinity to positive infinity. And even though if we look at the limits at 2 and at 0, what we will find, even though those limits exist, this function is not differentiable at those points. And why is that? Well, let's take a look at slope. Now, there's a special relationship. Whenever you have a line, if f of x is linear, of y is equal to mx plus b, what you have is the derivative is just equal to the slope of the line. And that's because of the definition of the derivative. What is the slope of the tangent line? It's just the slope of the line. Because as you can see, there's no curve with this. So the slope of the tangent line is just the entire slope of this line. So to draw this slope, it would look like this. At -1, the slope of this first part of the line is equal to -1. So from here going on forever, the slope of the tangent line is always going to equal -1. That's what that looks like. In reality, what that means is everything in this range has a slope of the tangent line is equal to the slope of the original line, which is equal to -1. For the second part of this function, x plus 4, that happens in the middle range between -2 and 0. Now for this, again, what is the slope there? The slope in this region is m is equal to 1. The graph of that for the derivative, because this one is included, has endpoints colored in. So those are your values from here to here. And again, the slope of the tangent line is the slope of a line. And then the last one has a slope of -1/2. So everything inside the last region has a slope of -1/2. And that's the slope in the region here. So this brings us to an important question, is where is this graph differentiable? And if I look at this, both at -2 and at 0, the graph is not differentiable. And the reason that is the slope abruptly changes. Here, coming in towards -2, the slope is equal to 1. At -2, the slope is equal to 1. So this corner here, where the slopes radically change, those two mean that at -2, the graph is not differentiable. Same thing up here at 0. The slope in the blue range is equal to 1. The slope coming down in the green is -1/2. But that abrupt change between the two slope values mean at 0, the graph is not differentiable. Now, this is an example of a graph that has something that's called a cusp. And it starts off like what you would imagine. This on the right-hand side is your square root function. But because I have the absolute value equal underneath the radical, I also have the left side of the function. Now, the question is, what is happening inside here? This idea of where it comes in like this and reaches this kind of like a point inside here, this is a cusp. So from a purely geometric point of view, what we have here is a vertical tangent. And we'll talk about this more and why it happens, but anytime you have a cusp like this, the graph is not differentiable at this point. So to sum up, we have 3 ways that a graph is not differentiable at a point. Okay, so first, if the function is not continuous. The second is if f has a corner. Think piecewise function. And then the third is if it has a vertical tangent.